Hello everyone, welcome to my channel. In this tutorial we are going to solve a plate with hole with hyperelastic material model. In this case we have taken a sinorini material model, hyperelastic material model. Now we'll see the geometry dimension. We have taken a plate with hole of a rectangle. Dimension is 10 meter and height is 5 meter. It has a thickness of 1 meter and the hole radius is 1 meter at the center. Now we'll see the material property. We have taken a rubber with a material of sinorini material model with a constant of C10, C01 and C20. One more property we need to specify, that is a Poisson ratio. .49. To define a sinorini material model in code Aster, we need to define three constants. One is C10, C20 and C01. I have taken a rubber in this. This is the constant I have taken. Now we'll solve this case using this boundary condition. Left side we are going to fix it, right side we are going to apply a displacement of 5 meter. Now we'll see how we are getting strain and stresses. Now just go to code Aster. I'm just opening salome. Geometry model. First we'll create a geometry using a box construction. This one is a 10 meter. In y direction it is in 5 and z direction it is in 1. Go to fit screen, x-axis fit. This is our model. Just apply and close. Now we need to create a hole. For that I am going to use a cylinder construction. Vector is OZ, radius is also 1 meter, thickness also 1 meter. Now here you can see x-axis OZ actually. So x-axis vector is OZ. Now just apply and close. Now we need to translate the cylinder. Go to operation, transformation, translation. In x direction we need to translate in 5, y direction we need to translate in 2.5. Just apply and close. Now we'll cut the cylinder from the box. Select this box one, go to operation, boolean, cut. Translation 1, just apply and close. Now simply we have created this plate with hole. Now we'll use this cut one for final geometry. Now before that we'll save this file. Just Ctrl S, just navigate the file into our proper folder. The folder name has to be named without space, otherwise it will show error while setting up the case in code Aster. This case is the 59th case sinorini model. Just save it. Now we'll create a groups to apply the boundary conditions. Left side is fixed, right side we need to apply a displacement. Go to mesh, create mesh. I'm going to use a simple tut mesh using NetGen algorithm, NetGen 3D parameter. Instead we can go for simple 3D parameter. Here I'm going to give element size of 0.3, just OK and apply and close. Just right click this mesh one and compute it. Now we have generated the mesh. Now we'll save this file. We'll move into Aster studies to create the setup. Just save OK. First select this current case, right click and add a stage. Now we need to read the mesh, read mesh. Choose the mesh one, tick this mesh file med, just apply and OK. Now just go to model definition, assign a finite element model everywhere. This is a mechanic model and 3D model. Just OK, apply and OK. Now we need to define the material. Go to define material. There is an option called Elas Hyper. Edit it. In Poisson ratio is 0.49. Now we need to define these constants one by one. First one is C10. C10 is 5.365. And C01 minus 2.477. And another one is 6.337. Now we will check the value again. 5.365 minus 2.477, 6.337. Now we have defined the properties correctly. 6.337 e power minus 1. E minus 1. Density, any property we can specify. I am just giving a steel density. Anyway, the constant and Poisson ratio is the important property. Just save OK. Just apply and OK. Now we have defined the material. Finally, we need to assign the material to the model. Everywhere we have assigned the material to the model. Just apply and OK. Now just go to functions and list to create the multiplication function. First define a function. Any name we can give. Just to understanding, I'm just giving load underscore f, load multiplication function. This one is the time. Edit. When the time is 0, the load is 0. Similarly, when the time is 1, the load is 1. That is the way we are going to apply a load multiplication factor. Then just apply and save OK. Now again go here. We need to specify the time period. Debut is 0, that is nothing but start, until 1. Number of substep is 0.1. 10 iteration I'm setting up. Just apply and OK. Now we need to specify the scheme, time or scheme, method, auto method, edit. Just save OK. Just apply and OK. Now just go to boundary condition load. Assign a mechanical load. Group of element, fixed one. Just save OK. Blockage we can give. Complete displacement is fixed. Just apply and OK. Now we can rename this into BC. Just apply and OK. Now again go to BC and loads. Assign a mechanical load. Enforce degree of freedom. The second boundary condition is we need to apply a displacement of 5 meter. In x direction it is in 5 meter. The group of element where we need to apply is displacement. Just save OK. Just again OK. Just apply and OK. Now we have fixed one side and other side we are applying a displacement of 5 meter. Now we need to create the solver, static nonlinear solver. List here. Just save OK. Here we need to go for loads. First load is a BC. Just save OK. Second one is the load 0 with the multiplication factor. Save OK. Just apply. Now here there is an option called compartment. Go to edit. Relation and deformation we need to set up. In relation it has to be hyperelastic, and deformation is a large deformation and rotation. Just save OK. Convergence also we can increase. Global iteration is 15 iteration. We can give 100 also. just say OK, just apply and OK. Now I have created the solver. Then I just want to create post processing. Reuse the input object. Here constraint deformation criteria. In constraint you choose sigma element, sigma node. In deformation just create EPSI element, EPSI node. In criteria just choose SIEQ element, SIEQ node. That's it. Just apply it, say OK. Now just save the result in specified format. I just want to save the result using set output results, pictures, code Aster, sinorini. I am giving a result of result 123 dot rmed. Just save. Here just go to edit. In results choose calchamp. There is option called tut-58, make it S. Save OK. In MID format just apply and OK. Now we have created the setup to solve the nonlinear material. Now we will go for solving. Just go to history view. Before that just save this file. Just click this plus button. Give some more memory to solve this case. And make this iteration auto refresh as 5 seconds. And just click this run. It will take some time to solve this case. Now the message file, it shows that it is completed the reading of command file. Next 5 seconds we can see it is completed around 9th iteration of 0.9. Now it has completed without any error. Now you can check it at the command file also. Here you can see diagnostic job is OK without any error. Now we can save it. Now we can use the Paraview to do the post processing. Just open home, pictures, code Aster. Now we are using a 59th sinorini, result 123. Just save OK, just apply it. Now choose displacement. First simulate it. Now we just change this into strain value. Now again come back into displacement. Now displacement is 5 meter. We are applying. We can check with the displacement X. Now we can move into stress also. Von Mises stress. In sinorini model we can say this stress is around 43. Mooney Revelin is the minimum stress value it is showing is a 16. In New Ocean model we have seen the stress value of 22. In this sinorini model we are seeing the stress value of around 43. Similarly we can check with the strain also. This is the strain in X direction. Maximum strain we are getting 1. Now we can plot or we can simulate one by one. Now we can see the results in proper color with using blue to red rainbow. Just apply and close. Here just make it 12. Now we can animate this also. This way is going to animate. Now we can see the stress value also using animation. We can set the color into blue to red rainbow with the 12 points. The final one is this one. The maximum stress we are getting here. minimum stress we are getting here. We can change the background using this palette also, gradient background. Similarly, we can go for sigma. It's a directional stresses. We can check with the sigma xx. We can change the color into blue to red rainbow. Just close it. This value make it 12. This also we can animate it. Here I have given loop, that's why it's animating like this. Okay, now we can plot stress strain curve using plot options. Now I have just selected these 3 nodes. Go to filter, search, type plot. You can get plot data over a time. Just enter it. Just apply it. Now we'll get this plot. Just here variable, just untick it. First to displacement we check it. Here it will show average value, quarantine range values, maximum value we have to check it. Here we can see we are applying when time is 0, the load displacement is 0. When time is 1, we are applying a displacement of 5 meter. Now we'll check the stress value also, how the stress is changing. Instead of displacement, we can change this into 1 meter stress. Just go to fit. So this is the way stress is getting increasing. When time is 0, the stress is 0. When time is 1, the stress is maximum of or more than 42, 43 we are getting. Now we can change this x-axis, y-axis to do the stress strain plot. In x-array name, change this into strain. X is a strain in stress state curve. Y is the 1 meter stress. Just fit screen. So x is the strain and y is the 1 meter stress. This is the way stress strain curve we are getting. Now we can change this into stress versus strain. This is a linear hyperelastic material. Within the elastic minute is behaving as a non-linear. Within the elastic minute, the behavior is a non-linear. That's why we are call it as hyperelastic material. Now we have completed this tutorial. Thank you for watching my videos. Please subscribe my channel for more videos. Thank you.